So stoichiometry is a study of quantitative aspects of chemical reactions. Quantitative means quantity, which means you're going to be measuring out different reactants to make the right combinations. So stoichiometry is just the science, if you will, of the study, like how much to add, how much you're going to get out. And stoichiometry literally has its laurels, if you will, on the principles of that conservation of matter or law of mass action. You have to know what goes in, you have to know what comes out, and everything has to be balanced. If you have a reaction like this one, for the 4 aluminums and 3 oxygens make 2 aluminum oxide, you have actually different ratios that you can use to make this kind of stoichiometry stuff possible. Now, remembering that that reaction means 4 moles of aluminum and 3 moles of oxygen make 2 moles of aluminum oxide, you can get all kinds of different ratios. And for this particular reaction, there are 6 different ratios. So you have, for example, a 4 mole aluminum to 3 mole oxygen relationship, which is what that first one is right there that I put a star next to. So if you were starting with moles of oxygen, you could figure out how many moles of aluminum were needed using this particular ratio right here. Again, you want to cancel what you start with, moles of oxygen, to get what you're looking for, moles of aluminum. That's what you need. On the other hand, if you have so many moles of aluminum and you want to know how many moles of oxygen you need, then you'd use the lower one, this one right here, because now moles of aluminum are on the bottom, moles of oxygen are on the top. So you can let these play any way you want. If you start with moles of aluminum, and you want to find moles of oxygen, use this one right here. On the other hand, if you have moles of aluminum and you're curious how much product, Al2O3, you can make, then you'd want to use this one right here. All right, because moles of aluminum on the bottom, moles of aluminum oxide on the top. And so all of these can be really helpful, and you can pick and play which one works for what you're doing. These are nothing more than relationships based on the balanced reaction. The 4 is the only number you see in front of the alumina, for example, and the 3 is the only number you see in front of the oxygen. All right, so you just keep going by using what you're wanting, and you can do all kinds of neat things. This is how chemists figure out like the quantities that are needed to make certain products, and also how much product is going to be made. Just like in cooking, if you have, so many cups of flour, you can figure out how many cookies you're going to make. Well, if we have so many moles of aluminum, we can figure out how many moles of aluminum oxide we're going to make, etc., etc. Ammonia is prepared by the reaction. Nitrogen plus 3 hydrogen makes 2 ammonia. And let's say that we have 10 moles of hydrogen with an excess of nitrogen, which just means we have more nitrogen than we know what to do with. Which stoichiometric factor would we use to find the moles of ammonia? So again, the key part here is that we're starting with moles of hydrogen. And like we talked about earlier, the thing you start with is going to go on the bottom, all right? And what you're looking for is going to be the part that goes on top, and that's going to be moles of ammonia. Now there's a 2 in front of the ammonia, so it's going to be 2 moles NH3 on top, and we're starting with hydrogen. Hydrogen has a 3 in front of it, 3 moles H2 on the bottom, 2 over 3, it's going to be answer D. All right. Now remember, a balanced reaction always shows the correct mole ratio. So it's always going to have a 2 by the moles of NH3 and a 3 by the moles of H2. And because we're starting with H2, we want the moles of H2 to cancel. So H2 is going to be on the bottom. NH3, what we're looking for, is going to be on the top. You would take that 10 moles and essentially multiply by 2 over 3 to turn moles of hydrogen that you're starting with into moles of ammonia you're going to get out. And this is, again, where chemists get paid, because some people really do need ammonia. This is one way to figure out how much you would make. Here's an example, again, of how the chemists get paid, if you will. And this reaction involves a compound called ammonium nitrate. Ammonium is NH4 plus. If you take ammonia, NH3, and add an H plus to it, it makes ammonium. Nitrate, NO3 minus. So they're both polyatomic ions, but they're both positive, negative 1, so they come together 1 to 1. Anyway, let's say we have a pound, which is nothing you need to know, but it's 454 grams. There's about 454 grams in a pound. So we've got 454 grams of this ammonium nitrate that decomposes. It breaks down. And the question is how much dinitrogen monoxide, N2O, and water are formed. And then it also says what's the theoretical yield of products. Okay, to answer a question like this, we need, of course, something so important for this chapter, and you probably guessed it. Yeah, the balanced reaction. And it appears that the balanced reaction is going to have ammonium nitrate as the reactant and N2O and water as products. So let's figure out what the relationship is going to be. And you can see how ammonium nitrate has 2 nitrogens in it, just like N2O has 2 nitrogens in it. However, there is a lot of hydrogen, 4 hydrogens in the ammonium, so we're going to need 2 waters. So in this balanced reaction, we would have 1 ammonium nitrate as a reactant, and that would break down into N2O and 2 waters as products. And all of the atoms are balanced. I encourage you to double check me if you don't believe me, and that's totally fine. I completely understand. We are good to go. But anyway, the first step in a lot of these reactions, find the balanced chemical reaction. So now if we want to figure out the yields or whatever of the N2O and water, which are the products, by the way, we're going to have to use that mole ratio. And so the 454 grams of ammonium nitrate, we can't leave it as that. We've got to turn it into moles. Now ammonium nitrate, if you figure out the molar mass, is 80.04. So again, to get that number, I took 2 nitrogens, and each nitrogen on the periodic table is about 14 grams per mole. I also added 4 hydrogens. Hydrogen's about 1 gram per mole, so that's 4 times 1. And I added that to 3 oxygens. Oxygen's about 16 grams per mole in the periodic table, so 16 times 3. So 2 times 14 plus 4 times 1 plus 3 times 16 is about 80. And to better sig figs, and I'm doing verbally right now, 80.04 is what you get to the 100th. And that number is the grams per mole, the molar mass of ammonium nitrate. So if we want to turn grams of ammonium nitrate into moles, we're going to divide 454 by 80.04. And you can see that the grams will cancel out. We'll have moles, 3 sig figs in 454. So the answer to 3 sig figs, 5.68 moles ammonium nitrate. So 454 grams ammonium nitrate represents 5.68 moles of ammonium nitrate. Next step, now that we have the moles of reactant, let's convert the moles of the reactant into moles of the product. And this is where the balanced chemical reaction kicks in. And again, we can use any ratio we want to based on this reaction. So we could use 1 mole of NH4NaO3 to 1 mole N2O because they both have 1s in front of them. We could also use the relationship of 1 NH4NO3 to 2 moles of water because of the 1 to 2. And really, you can do N2O first or you can do water first. It doesn't matter. I think in this example, I did water first, all right? And you don't have to, but it's totally fine. And if you're going to do water, you need a stoichiometric factor, which is just the ratio of moles in the reaction. So for this one, because we're starting with ammonium nitrate, we want ammonium nitrate on the bottom and water on the top. So there's a 1 in front of the NH4NO3 and a 2 in front of the water. We're going to use a factor of 2 to 1. And that says that 2 moles of water are created or produced for every 1 mole of ammonium nitrate that's used up. This, my friends, is the power of the balanced chemical reaction. To get that 2 to 1 ratio is really important. If you didn't have that 2 to 1 ratio, everything would come up kind of messy. You wouldn't have the right answer and you'd end up with weird things. So knowing this relationship, this stoichiometric factor, super important. Now, once you have the factor, then you can just take that 5.68 moles and multiply it. Because remember, it's 5.68 moles ammonium nitrate. You can see how the moles of ammonium nitrate cancel, and you'll have then just moles of water. So 5.68 times 2 to 3 significant figures, 11.4 moles of water are produced. Now, this is kind of cool for a chemist, because here you've got 454 grams of ammonium nitrate just staring at you, and it's like, what are you going to do? Well, you can actually calculate how much moles, anyway, of water are going to come out using these steps. The grams to moles is what we've done so far. The grams to moles use the molar mass of ammonium nitrate, and then the moles to moles is just the relationship from the balanced reaction. If you're going to do moles of N2O, the other product, all right, notice how N2O and NH4NO3 are both relationships of 1 to 1. Like it's 1 mole ammonium nitrate makes 1 mole of N2O. So if you had 5.68 moles ammonium nitrate, you will make 5.68 moles of N2O. The ratio is different. That's why you have a different answer than you did for water. You're going to end up with twice as many moles of water as you do the N2O. We talked earlier about moles, but honestly, most people like to know things in mass, which is grams or pounds or kilograms. I joke because I don't really like the English units, but anyway, that's fine. They want to know kilograms and grams and pounds and stuff like that. Tons, all right. Anyway, I digress. Now, the number we're going to calculate here has a fancy name, and it's called theoretical yield, and it's how much of the product should be created. Notice I'm emphasizing there the should. We'll talk about that later. So the theoretical yield of these things is just how much should be created. So for water, if you wanted to know the theoretical yield of water, 11.4 moles of water times the molar mass. And again, for 18.02, that came from 1 oxygen and 2 hydrogen, or 1 times 16 plus 2 times hydrogen is about 18 grams per mole. You should be making 204 grams of water. So theoretically, in this reaction, if you put 454 grams of ammonium nitrate in and it all reacts, you will be making 204 grams of water. That's the theoretical yield of water in this reaction. This is what I call the grams, moles, grams dance. And we're going to do this a lot in chemistry. Grams to moles to moles to grams. So grams to moles, we took the original grams, turned them into moles of ammonium nitrate. Then the moles to moles part is where the balanced chemical reaction comes in. For water, it was 2 moles of water for every 1 mole ammonium nitrate. And then finally, moles to grams, we're turning it back from moles into grams. So in this case, water's molar mass, 18.02 grams per mole. That's how we got the 204. You can't really go straight from grams to grams. You have to do the grams to moles to moles to grams at least once to see what's happening. Now, there is another product, though, N2O. And if you're curious how much N2O is formed, you can totally do the grams to moles to moles to grams. Now, we saw earlier that you had, I think it was 5.68 moles of N2O because of the 1-to-1 ratio ammonium nitrate. And from there, you could find the molar mass of N2O, and you could multiply the moles by the molar mass to get the grams, and that would be fine. However, law of mass action has a little trick that sometimes is used. Now, if we put 454 grams of ammonium nitrate and matter cannot be created or destroyed, that means that on the product side, we're going to have a total of 454 grams. And we already calculated that there's 204 grams of water created. So notice that 204 is a lot less than 454. Where did all the rest of the mass go, Dr. Russell? Oh, thank you, whoever asked in the back of the room. Yeah, the other mass is N2O. So all you have to do really on this problem is take the total mass you started with, 454, subtract the grams of water, which you calculated 204, and you should be able to figure out that the N2O that's created, 250 grams. And notice the dot by the 0, that means that's a significant number. That's a 3 sig fig number. Now, you don't have to do it this way. You could also take the moles of N2O and turn it into grams, and that would be fine too, but I am trying to teach you all my lazy chemist techniques. Here's the opposite way. N2O is about 44.01 grams per mole, all right? And if you do that, then that comes out to be 5.68 moles times 44.01, 250 grams. Nitrogen's about 14 grams per mole, and there's 2 of them, so that's 28. 28 plus 16, 28, 38 would be 44 grams per mole, and to better sig figs, that's what you got. So you have more than one way to do this kind of problem. Now, the latter way, the way that's done at the bottom, will always work. The top way, law of mass action, you have to be careful. There's some tricks we're going to talk about. So if in doubt, I do encourage you to do grams to moles to moles to grams, which would be like this part right here. On the other hand, law of mass action is a lot easier if you can get it to work, and we'll talk about when it works and when it doesn't work in a bit. This is something that sometimes people like. It's a diagram. Now, remembering that all the mass has to be accounted for, all right? In this reaction, ammonium nitrate makes N2O and H2O. So we started with 454 grams, which we then figured out was 5.68 moles. And in this reaction, all of the ammonium nitrate is reacted. So the change, how much it goes up or down, minus 5.68. And there's nothing left at the end, all right? But the matter has to go somewhere. So the 5.68 moles of ammonium nitrate made a 1-to-1 or 5.68 moles of N2O, and 2 times that number, 2 times 5.68 moles of water. So at the end of this reaction, 5.68 moles N2O and 11.4 moles of water, and multiplying both of those numbers by their molar masses, 250 grams of N2O, 204 grams of water. And you add those numbers up, sure enough, it equals the mass you started with. Mass is conserved. So if these two numbers and the number I circled earlier are equal, you are good to go and you are following law of mass action. Woohoo! We calculated the theoretical yield earlier of water and of N2O. And by hook or crook, by a crook, we figured out that N2O, that theoretical yield, how much we should have gotten out, 250 grams. And remember, it's 250 dots, so that's 3 sig figs. What happens a lot, though, in chemistry is that even though you should have made 250 grams, you only made, in this case, 131 grams. Now, N2O is a gas, and it's easy to have a leak in the valve or something like that, and some of the N2O goes away. It's also possible that the N2O was reacting with something else. There was like some kind of weird secondary reaction. There's lots of reasons why the actual yield, which is how much we actually got out, is not the same as the theoretical yield. And if you've ever been like cooking and maybe making cookies or something like that, maybe you, oh man, accidentally dropped cookie dough on the ground and the dog ate it. All right. That would be a real life example of when a regular recipe went bad. In my case, it would probably be because I was eating the cookie dough, which I do like a lot, I confess. So I didn't make as many cookies as I wanted. So there's lots of silly reasons and also very good science reasons why the actual yield, how much you actually ended up with, was less than what you should have ended up with. So in this not as exciting as cookie example, we should have had 250 grams of N2O. We only ended up with 131. So percent yield is something that chemists use a lot to figure out how effective your method of making N2O is, all right? And the percent yield just compares the actual yield to the theoretical yield. And it's a percentage, so it's usually less than 100%, stuff like that. Percent yield is equal to actual yield divided by theoretical yield times 100%. So in this example, we should have had 250 grams. And for whatever reason, scientific or otherwise, we only ended up with 131 grams. So the percent yield, actual divided by theoretical times 100, 131 divided by 250 times 100%, this reaction had a 52.4% 50% yield of the dinitrogen monoxide, the N2O. That could be really good. It could be really bad. We don't know enough about the reaction to make those kind of designations. But we can at least say that, hey, in this reaction, we had a little bit more than 50% yield of our N2O. Now, if the lab across the street has a way to make like 75% yield consistently, that might be like a better process to make the N2O. This is how percent yields can be used. And again, don't think of percent yields as like 90% or higher is an A and 80% to 89 is a B, that kind of stuff. One time in graduate school, I had a percent yield on a transformation of a chromium compound from kind of a blue to kind of a purple. And I was so excited, I like called my parents, and it was like 4 a.m. And they were like, oh man, you need to get back to sleep, which was probably true, let's be honest. But anyway, I was so excited, and my percent yield for that transformation was like 5%. It was so low, okay? But it was exciting because I was the first person who had ever done it, all right? And that was pretty cool. And the first time you do something, it's always harder than subsequent times, at least usually. So yeah, that was a really low yield. No one gave me an F because that was the first time it had been done, and that was pretty cool. So don't think about these as A, B, C, D, F kind of ratios. 52.4% could be outstanding, or it could be horrible. We just don't know. We have to know more about the chemistry to make those kind of calls. This is a reaction. It should have created 74.0 grams, but for whatever reason, we only ended up with 29.1 grams of product. And the question is, calculate the percent yield. So again, it's actual divided by theoretical. We actually only ended up with 29.1 grams. We should have ended up with 74 grams. So in your calculator, 29.1 divided by 74.0, it comes out to be answer E, 39.3%. That would be the percent yield for this reaction. Once in a while, percent yields are greater than 100%. Those mean usually that the product is contaminated. A lot of times if you have a wet sample, like with water, the water adds on and that will add mass. You should never have a negative percent yield. So if you get a negative, something's wrong. But and most of the time, percent yields will be less than 100%.